Good afternoon, ladies and gentlemen. The current situation in the forging industry worldwide, combined with fast technical progress, makes companies looking for new technologies in order to decrease the production costs and stay competitive. In the same time, the requirements to the quality and endurance of materials get stricter. In the first instance, it's applicable to special alloys and steels produced mainly by forging on hydraulic forging presses. Due to big diversity of such materials, a number of forging technologies using 4-die forging device for forging presses has also boosted, as well as increased the number of possible design solutions for these forging tools. These short animation video is shown to get acquainted with this forging tool and technique for those of you who didn't see it before. A development of process technology to produce forgings is carried out individually. Development of process technology to introduce forgings always precedes the work to design and manufacture FDFD. The development of new design solution and forging technology is carried out individually for every customer after a detailed study of his forging technology and production process details. Such technology includes the following main steps: ingot heating, rough forging, calibration forging, reheating if required, cutting and heat treatment of forgings. And the key point of this technology is forging in FDFD. Our finite element method-based calculations show that during 4-die forging in FDFD, it's possible to increase the deformation ratio at each single reduction pass by several times in comparison with conventional forging between 2 dies without obtaining the cracks or splitting fractures in a workpiece. Due to the unique dice movement schedule and reductions performed with high deformation ratios, a significantly higher metal quality is achieved. Such quality is impossible to obtain with other forging technologies. Forging technologies for FDFD have different reduction schedules. Let us review 2 of them: forging without metal spreading between dies and forging with metal spreading between dies. As per the first schedule, without metal spreading between dies, a workpiece is turned after each pass at 45 degrees around its long axis to ensure the deformation of its entire surface starting from the second pass. The second schedule is a new and more effective forging scheme, as the forging being performed with higher deformation ratios, and it's accompanied by the spreading the metal between the dies. These allows treating an ingot cut structure more intensively, and results into the intensification of additional supplementary shear strains at this area of a workpiece. Displaced material at the next reduction is pressed again into the workpiece, and shear strains spread across the total cross-sectional area of the workpiece. Besides, all the reductions performed during every single forging pass are acting so that the cross-section of the forged part is permanently displaced in relation to the initial workpiece cross-section in one and the same circumferential direction. This leads to actual twisting of metal structure and improvement of its quality. The respective FDFD forging schedule with twisting of metal macrostructure is shown at the previous slide. Upon the results of industrial trials, it was established that the combination of shear strains due to the workpiece reduction between the dies and shear strains resulting from the workpiece section by section turning performed by manipulators provides a considerable improvement of metal quality. Cool down of the ingots during 2 dies forging leads to unavoidable reheatings. But using the forging schedules for FDFD involving supplementary shear strains, it's possible to relatively easily maintain the workpiece material temperature within the required forging temperature range due to deformation heating of the area. Industrial trials performed on 5, 20, and 25 meganewton presses prove that such forging schedules provide conditions approaching isothermal ones when forging in FDFD. Traditionally, long-axis forgings made of titanium alloys and other special steels and alloys are produced in hydraulic forging presses or radial forging machines by stretch forging ingots or predeformed blanks. The 4-die forging method using RFM is more productive process when compared to conventional 2-die stretch forging. However, a major disadvantage associated with the RFMs is the high cost of equipment with a narrow specialization, mainly for stretch forging operations. In contrast, a forging press is multi-purpose equipment, and in addition to stretch forging, it can be used for a variety of other operations, such as upsetting, cutting, rolling, etc. Also, the main advantage of the forging using presses in comparison when forging in RFMs is that the quality of metal forged in the presses is higher than the same parameter for RFMs. Based on these advantages offered by forging presses, 4-die forging devices were developed in the late 20th century and early 21st century for installation in hydraulic presses to forge ingots and blanks made of different steels and special alloys. A comparative table for two technologies of forging an ingot is shown here for your attention. First technology is for forging of the ingot using 2 dies. Second technology is for forging the same ingot in 4-die forging device using the dies with concave surfaces. When an ingot is forged between 2 dies, technology number 1, it quickly cools down, so after the 9th pass, a workpiece is sent for heating. As shown in the table, an ingot of 4,300 kilograms is forged in 23 passes, and the total time, excluding time required for workpiece reheating and dies changing, is 1,195 seconds. When forging the same ingot in FDFD, it's technology number 2, the amount of passes is only 11, and the forging time is 587 seconds, which is 2 times less compared to conventional technique. Furthermore, an additional reheating as well as dies change for calibration are not necessary, since the same set of dies having concave surfaces is used for both rough forging, 1st to 9th passes, and for calibration, last 2 passes. Also, a new calibration method for forging in FDFD and the respective special tools for this purpose have been developed and tested. In this method, the dies with concave working surfaces are used, so that the closed dies form a cylinder-shaped base space in between. Both rough and finish forging operations are performed using the same dies. A 4-die forging device with a set of dies having concave surfaces can also be successfully used only for finishing operations. Just one FDFD for calibration operations of workpieces with diameters from 180 to 500 millimeter and having 3 die sets can replace up to 15 blocks of 2 concave dies with springs between them, which are usually used for calibration at many forging companies. In this case, FDFD for calibration has compact sizes and its cost is significantly less than the total cost of all these die blocks. As I have told before, in each and every case, a selection of FDFD design and depends upon technological process peculiarities, form, size, and material of a workpiece and forging, and also upon the design of forging press. We apply individual approach to each and every customer and propose the most appropriate forging technology and design solutions for FDFD. New design solutions for FDFD have no lubrication systems. Different versions of self-lubricated slider bearings are used instead. Service experience gained for several FDFDs with self-lubricating slider bearing systems prove their high reliability, ease of operation, cost effectiveness, and environmental friendliness during the long run of these devices. Also, die cooling systems are also currently rarely applied, except for the devices used for forging the large batches of carbon and low alloy steel products, like railway access or for locomotives and carriages. FDFD service experience has been analyzed, and as a result, new improved techniques and design solutions have been developed for quick change of the dies, which is shown on this slide. One of such solution is application of snap-type clamps. A sample die set is moved into the work zone of the manipulator. Then, with the help of manipulator, a set of dies is placed into the working zone of FDFD. Device holders are brought together by means of forging press top cross beam movement so that the device holders press onto the die bearing surfaces. Hence, the snaps get actuated to grip the dies. Thereafter, the U-shaped ties shall be taken out of the holes in FDFD dies, and device is ready for operation. For forging ingots and blanks with diameter up to 450 millimeters, FDFD design solution is proposed where there is no connection of device top body to the press movable crossbeam. Springs and guiding columns are employed to bring the dies apart in this solution. Spring type FDFD can be much easier adapted to any existing press design and also to any forging technology. A device of such type can be brought into the press working zone within a few seconds, and the same short time is required to take the device out from the press. For forging ingots and blanks with diameter more than 450 millimeters, FDFD design solution has also been developed, which includes a system of non-rigid quick connection of the device to the press crossbeam or to the top die. Such FDFD has catches to quickly connect the device to press crossbeam or to the top die and quickly disconnect device from it. A mechanism used to actuate the catches is driven by electric motor or manually, whatever is better for customer. So this slide shows one of our new solutions for forging device for obtaining the square and rectangular cross-section forgings. So therefore, after 20 years of FDFD operation, we have developed and patented plenty of different design solutions and forging technologies for hydraulic presses. For these years, a number of new FDFD design solutions was developed. Sorry, come back. Hello. Yeah, so for all these years, a number of new FDFD solutions was developed for the presses in capacities from 5 to 120 meganewtons and for 1.25 meganewton radial forging machine. All these devices were manufactured and put into industrial operation, and the experience gained by these companies confirms that high quality and high productivity when producing forgings in die forging device. Based on the accumulated experience and investing into R&D. Sorry, can you make this video live?
Video.
It's bad. No, well, sorry. This video can also be found on YouTube if you type FDFD or 4-die forging. So based on the accumulated experience and investing into R&D activities, the author of this report and paper continuously work at further improvements of the FD design, developing new technologies and new solutions for particular production applications and respective forging technologies. Also, all these streamlining activities aim to reduce the customer forging costs and eliminate non-operational wastes. Thanks for your attention.